All right, continuing in our course packet, the next thing we're going into is acidity effects, qualitative acidity effects in a row of atoms. So whether it's carbon, hydrogen, nitrogen, hydrogen, oxygen, hydrogen, or fluorine, hydrogen bond, which of those is going to be qualitatively the most acidic? So we have an example right here. The question that I'm asking here is, what's the stronger acid? What's the stronger acid? Water? So let's say stronger acid question mark. What's the stronger acid, water or ammonia right there? It turns out that when we're talking about atoms in the same row, the major effect is based on their electronegativity. So it's controlled by electronegativity, EN, electronegativity. So what I want you to do right now is just take a minute to think about it for yourself. Let's go ahead and draw the arrows for the proton transfer, the conjugate acids and bases for this one versus that one over in this box, and then think about it. Think about what the factor of electronegativity would have on this. So you pause the video, you're doing that right now, you're back. Okay, so we want to draw the conjugate acid, conjugate base. We're going to transfer a proton from these two acids to our bases. We can show that flow of electrons. The base is going to supply those electrons. It's going to be attracted to the partial positive on these hydrogens to give BH as the conjugate acid and OH minus the conjugate base. Same thing would happen with ammonia. We would transfer the proton to BH, and that would leave us with NH2 minus. So which one was a stronger acid? Well, what we do know is that electronegativity, that the trend is that the top right of the periodic table has the most electronegative atoms. So of these four that we've shown right here, fluorine's the most electronegative, carbon's the least electronegative, and we know that oxygen is more electronegative than nitrogen then. So how can that explain the acidity trend? How does that explain the acidity trend? Well, we can think about it in multiple ways. One way is just the impact on the acid. So if we think about why this hydrogen's acidic, why this hydrogen's acidic, well, acids are giving up a proton. A proton is positively charged. So there must be a partial positive on these hydrogens that makes them acidic. And why is there a partial positive there? Because they are attached to a more electronegative atom. So both the oxygen and the nitrogen, are pulling electron density away from them, creating that dipole. But which hydrogen is going to have a larger partial positive on itself? And since oxygen is the more electronegative atom, it's going to pull harder than nitrogen, so the partial negative on that is going to be larger, and the partial positive on that hydrogen is going to be larger. I'm just going to exaggerate it here. We'll show a small partial negative there and a small partial positive to indicate that this is a larger partial positive. It's a stronger acid because of that. B minus, the base, is going to be more attracted to the larger partial positive because negatives flow to positives. So looking at that by itself, that says that this is the stronger acid. What about if we look at the conjugate bases? So remember what we just said up a little higher on our note packet is that the stronger acid is connected to the more stable conjugate base. So we have to look at the conjugate bases, and one of them is OH minus versus NH2 minus. So which of these is more stable? The more stable conjugate base came from the stronger acid. Well, the negative charge is on a nitrogen versus an oxygen. The one that likes negative charge, that is more stable with negative charge, is going to be more stable holding that negative charge. So oxygen is more electronegative, so that is more stable. So because of that, that means that it came from the stronger acid. So that's how that works. So both, if we look at the acid itself or if we look at the conjugate base, both of those point to water being the stronger acid. How does that come out when we look at the actual numbers? Well, if we look at this row of acids, a carbon-hydrogen bond has a pKa around 60, NH has a pKa around 36, OH is around 16, FH is 3.1. So as we see that we have increasing electronegativity, we also have increasing acidity this way. Remember, lower pK values, stronger acids. So that's how it works within a row.